Hi, and welcome to a video where I want to work out some problems, some specific problems regarding entropy production for a closed system. All right, so let's get started and see where we go. So this video is going to pertain only to closed systems. I want to remember now, what is a closed system? Remember, that would be any system that's got a fixed mass. And I think for our course, probably the visualization of a closed system, the classic visualization is a gas that's contained inside a piston and cylinder, but it can be any fixed mass closed system. What I want to cover in this video is you need to be familiar with the difference between simply entropy and the term called entropy production. Those are two different things. And then going to get specific about entropy production for a closed system undergoing a process like 1 to 2. Okay. And then we'll have a couple of worked out examples for you. Crash course on entropy versus entropy production. Recall that just entropy, just letter S, is a property. So there's a number of properties that you're pretty familiar with already: pressure, volume, temperature, internal energy, enthalpy. Well, entropy is a property as well, a property that depends on the state of a closed system. Now, numerically, the way we remember the property entropy is if a closed system is highly ordered, high order is going to mean low entropy, okay, lack of disorder, okay. However, if a closed system has a high amount of disorder, okay, then the property entropy will have a high value, a high entropy. And that's enough, I think, to talk about the property that we call entropy, okay. And how do we define entropy? Well, don't worry, I'm not going to belabor this point, but in chapter 6, entropy change, S2 minus S1, is defined in terms of an integral for a process that involves heat transfer, okay? And so you're looking around a closed system boundary for heat transfer, and as long as you go from state 1 to state 2 along any reversible process from 1 to 2, that's the way you determine change in entropy. It's an integral of all heat transfer at whatever reservoir temperature you're transferring it at across any reversible path, 1 to 2. And the visualization of entropy change on a TS diagram for a reversible process, clip right out of your book. So as long as you can describe the path, the process path 1 to 2 on a TS diagram, you can visualize the change in entropy as well as the heat transfer. The heat transfer is visualized by the area under the curve, or in other words, the integral of TdS. So that's just a little crash course type words about change in entropy. And then we're going to move on now to what we call entropy production, something different, okay? Now, this is not the number 6. This is Greek letter sigma. And so in thermodynamics class, we use sigma to represent the phrase called entropy production, the production of entropy as a result of some process, 1 to 2 or 3 to 4. Screenshot out of your book, section 5.2.3, statements of entropy production, a definition of entropy production. Now, lots of words here on this slide. Entropy production, here's an equation. Entropy change of a closed system equals an entropy transfer term, more in a second, plus the amount of entropy produced as a result of the process, entropy production. Whew, that'll blow your mind. So let's move along from that. Okay. This is a visual repeat of equation 6.2 in your text, which is, it says entropy change equals entropy transfer as a result of heat crossing the boundary into or out of the closed system or open system, plus entropy production as a result of the process. All right, I got to tell you that I can best visualize and work with entropy production. This is what we're trying to figure out. In homework problems, this is what we're assigned to do. I like to get that on the left-hand side of the equation. So I'm going to solve for it. Entropy production, which is going to have to be greater, it's going to be a number greater than or equal to 0 to be a possible process. Entropy production equals entropy change minus entropy transfer. I find that easier to remember and easier to visualize. Visual statements of the second law. Sigma is greater than or equal to 0. If sigma is greater than or equal to 0, that means a proposed process is possible. It can be done. Now, if sigma is simply greater than 0, that means the process is possible and irreversible. There's some kind of irreversibilities going on in the process described. If sigma exactly equals 0, not only is the proposed process possible, but it is reversible. Now, if you go through a problem and you find that sigma is less than 0, numerically less than 0, as an engineer, you can state that that proposed process is impossible. It cannot work. It is impossible to create that proposed process. So the key, your job is to get good at quantifying what is sigma, what is the entropy production for this video for a closed system. Okay, and so here is equation 624, screenshot. The upper part is right out of the textbook. But what I like to do, I prefer solving for sigma because generally that's what you're looking to find. Sigma equals minus the integral of del Q over T, that little b, that says across the system boundary, the integral of del Q over T across the system boundary, that's the entropy transfer term, plus capital S2 minus capital S1, the entropy change of the closed system. Okay, so I'm simply taking 624 and I'm rearranging it to solve for sigma on the left side. Okay, and so you can see that S2 minus S1 is going to go to the right-hand side. Okay, and also we're going to have a minus sign associated with the integral. So it's simply doing the algebra to solve this equation 624 for this version of equation 624. Let's talk about some details of the entropy change term. Capital S2 minus capital S1 for a closed system. Capital S, that's an extensive property. Looking ahead towards homework problems and the example problem, the extensive property, capital S2 minus capital S1 is equal to the mass of the closed system times little s2 minus little s1. Okay, so simple as that. So those are details about the entropy change term, capital S2 minus capital S1. Now some details about the entropy transfer term. Okay, this is the toughest thing to work with. The integral of del Q over T, look for all occurrences of heat transfer across the system boundary B, across that dashed line where we started with a sketch. Rather than me reading these words on the slide to you, I believe the next slide has got a little example problem that hopefully will make it come into focus for you. Simple example of calculating the entropy transfer term. So here's the entropy transfer term, the integral from state 1 to state 2 of del Q over T across the system boundary. There's the dashed line. That's our system boundary. For this example, I've got 60 kilojoules of heat coming into the system, okay, from a temperature reservoir that's held at 300 degrees K. This is just an example, okay? So it's not general, it's an example, all right? How will I determine simply the entropy transfer term? I'm going to study my closed system. I see one instance of heat transfer. There it is. So I can do the integral, recognizing that Q positive value is N. Q positive is N. That's what I have on my example. So I've got plus 60 kilojoules in the numerator divided by the temperature at which I'm transferring the heat, 300 K. Denominator, 300 K. So there, the math is easy. 60 over 300 is 0.2 units, kilojoules per degree K. That's the result. That's the numerical result of the entropy transfer term. That's the way you do it. Okay, so with all of that crash course information, now let's look at example one that I'm going to show worked out numerically. Here it is. A gas has a mass of 2 kilograms. It's contained in a piston and cylinder. Heat in the amount of 80 kilojoules is added, Qn, from a heat source held at 400 K. During that process, the specific entropy of the gas increases by 0.25 kilojoules per kilogram degree K. The specific entropy increases. That means little s2 minus little s1 equals plus 0.25 kilojoules per kilogram K. And the problem is determine the entropy production sigma for this process. All right, here we go. We can fit it on one slide. Here's the problem statement. Here's a sketch, piston and cylinder. I'm showing heat in and work out of my closed system. There's my system boundary. And I'm showing that the heat is being added from a temperature source at 400 K. That's a good sketch, all right? Some notes that I write down next to my sketch. I write it's a closed system. I write down the mass. I write that heat is transferred into the closed system. That's going to help me with the entropy transfer term. I write down that S2 minus S1 is 0.2. I believe that is a typo. It should be 0.25 kilojoules per kilogram. So there's a typo, 0.25. Find sigma, entropy production, in kilojoules per degree K. So, all right, there we go. We go back to our crash course. What's entropy production? It is these two terms minus the entropy transfer plus the entropy change. I've only got to worry about, okay, so that's what I'm looking for, left-hand side, okay? I've just got to be careful with my mass, with my signs and my terms, okay? So I've got negative, pull my negative sign, integral del Q over T. In brackets, Q is going in, T is known, okay? Entropy change term, capital S2 minus capital S1 is the mass, given, times S2 minus S1, given, okay? All right, we're going to do the math, equals minus, in brackets, 80 over 400 plus 2 times 0.25. We'll do the math. The entropy production sigma equals plus, I've got a negative number and a positive number. I add those two together and I get plus 0.3 kilojoules per degree K. And that's kind of like, whoo, okay. It's possible. This is a possible but irreversible. So the homework problem defined here would be possible and irreversible since sigma is greater than 0. Not so bad for this example. Not so bad. Please excuse my typo, but I'm going to continue to blunder ahead. Second example, a gas with a mass of 0.5 kilogram is also contained in a piston cylinder. Heat in the amount of 40 kilojoules is rejected from the gas to the surroundings at 290 K. During the process, the specific entropy of the gas decreases by 0.2 kilojoules per kilogram degree K. Determine the entropy production sigma for this process. All right, here we go. Let's look at the sketch first. Okay. Piston and cylinder. I'm showing my little dashed line control surface. I've got one instance of heat transfer, but look at my sketch. I am showing heat going in, but I'm very careful on my sketch to clarify that Qn is less than 0. That's important. I'm showing that my heat, I'm exchanging heat with a heat source of 290 K. So actually my arrow is going out of the system. I'm showing it in just to try to keep myself straight. Okay, so we're going to go notes, closed system, mass 0.5 kilograms. I'm writing down in big letters, heat is rejected. I'm going to have Q negative. Entropy change is minus 0.2 kilojoules per kilogram per degree K. What am I supposed to find? Entropy production in kilojoules per degree K. All right, there's my expression. Entropy production for a closed system minus the integral of del Q over T across the boundary. Okay, that's where, okay, I'm going to have to be very careful. Del Q in is a negative number. All right, plus the entropy change, capital S2 minus capital S1. All right, now we're going to start putting in numbers. Okay, here's my entropy transfer term plus Qn over T. Let's look at the numerics. There's my minus sign. I've got to be very careful to pull down. In brackets, Qn is minus 40 kilojoules. The divisor, T, 290 K, plus the entropy change term, plus 0.5 kilograms times minus 0.2 kilojoules per kilogram degree K. Again, I do them. Oh, here we go. This is a positive number here, isn't it? That's a positive number. This is a negative number. I add them all up and I get plus 0.0379 kilojoules per degree K. Whew. My number is bigger than 0, so I've got a process that is possible and irreversible. Those are the two worked out problems that I hope helped you understand where to go, where to get started when you have homework problems that request that have a closed system and ask you for entropy production, not just change in entropy. That's delta S. Okay. You understand the difference between entropy change and entropy transfer and entropy production. Okay. Can you determine sigma for a closed system undergoing a process? I hope with these examples, you're in a lot better shape to do that. So there it is, two worked out problems, complete with a little crash course on entropy production. I'm getting ready to make the next video in which I'm going to talk about closed systems, but going through a special process called a cycle. And there's going to be some worked out example problems that I have for you for that as well.